Hello, everyone. Today we'll be representing our project, Trendify. This was completed as part of the deep learning course, and my name is Idan, and this is Amit.
Hello. Our main goal is to predict how popular a given song will be by leveraging two data modalities, the audio itself, represented by spectrograms, and textual metadata from sources like Spotify.
We want to predict a song's popularity using multimodal approach. We feed the spectrograms into a CNN to capture acoustic patterns, while textual data such as artist name, song title, and release date go into the transformer model. This is inspired by previous research on music genre classification using CNN and other techniques. Our unique twist is to target popularity, which can be seen as a regression, instead of a classification.
Before diving deeper, let's quickly define a spectrogram. A spectrogram is a visual representation of an audio signal's frequency content over time. Different frequencies are plotted on one axis, time on the other, and color intensity correspond to amplitude. By transforming audio into a 2D image format, we can apply image-based deep learning methods like CNN to find meaningful patterns. We rely on two main datasets, Billboard Hot 100 spectrograms, a Kaggle dataset containing CWT spectrograms, which capturing a lot of time frequency information. The second one is Spotify dataset, a large dataset containing textual fields like artist name, song title, release date, and popularity. And we'll aim to combine those two into a merged dataset that have both spectrogram and matching textual info. We also separately use the large Spotify dataset purely for text-based modeling on pre-training.
Working with these datasets presented, there are two major challenges. One is large and inconsistent spectrogram size. The width is around 40K pixels, which isn't standardized. So our solution is to downsample them using FFT interpolations, making it standardized to a fixed resolution. This preserves the important frequency patterns while drastically reducing the size. Another challenge is a small number of spectrogram samples. We only have 3K spectrogram is limiting. Our solution is to apply data augmentation, like adding a noise or masking random patches to improve robustness. We also rely on training the text-only model on a large Spotify dataset to help the transformer learn general textual patterns. Our architecture is multimodal, as we've seen. A CNN handles spectrograms, extracting time frequency features through convolution, pooling, batch normalization, and dropout. A transformer model from Hugging Face processes textual metadata, such as artist name, song name, and release year. We then fuse the high-level feature from both networks into a combined layer for a single popularity prediction. This approach let us compute both audio structure and contextual information.
The CNN is designed to capture complex spectral patterns. We have 3 convolution blocks with kernel that was chosen to capture special features. Each block contains spot-once convolution, batch normalization, max pooling, and dropout. Then a global average pooling layer goes into a fully connected layer. We can either output a single popularity regression value or produce a 64-dimensional feature vector that merge with the transformer into the combined model. For the textual metadata, we have one of the Hugging Faces model to tokenize and embed fields like songs, name, year, release, etc. Then a fully connected layers. The model can act standalone or be fused with the CNN, as we've seen before.
When we fuse the CNN transformer, each network outputs 64-dimensional vector. Then we concatenate them, resulting 128 vector. This goes to a fully connected layer. We produce a single regression. This combined for audio-derived features and textual content to predict a single popularity. Our first attempt involves training each component directly on a small merged dataset. First, the transform alone without audio. Then the second is CNN alone without text. The third one is combined CNN and transformer from scratch. We quickly realized 2 problems appear. The small dataset is not enough to train the large transformer effectively, and the ideal number of epochs is different for CNN and transformer, so training them jointly can be unoptimal.
We improve our strategy by pre-training each model separately on more appropriate data. The transformer is pre-trained on the large Spotify text data. The CNN is pre-trained on smaller spectrogram set with heavy augmentation for generalization. Once pre-trained, we freeze those early layers of each model and only learn the fused layer in the combined model. Advantage, including optimal training time and more expressive feature representation, since each submodel has already seen the data relevant to its domain. In summary, we have separated dataset as seen before. Our loss function is MSE. We use Adam as the optimizer, and we tune our hyperparameter using Optula.
There are some results we can see. The CNN alone got around this 32 accuracy. The transformer also is 42 test accuracy, and combined model is roughly 60 accuracy, which is still not good, but it's an improvement for combining them.
Next, we use the pre-train approach. The CNN pre-trained similarly, so the same accuracy. The transformer was trained on the huge Spotify dataset, which results in better test accuracy. Then the combined model tested on the merged dataset and yields around 62% accuracy. This number is a bit higher than the naive approach, showing that pre-trained helps.
To wrap up, the multimodal approach combining audio spectrogram and text metadata generally yields better results than alone. For spectrograms, images, carefully downsample is better than random cropping, and data augmentation boosts performance. Per-training each model separately can solve data mismatch problems. Finally, if your submodel needs a different epoch schedule, training them separately can be better.
Looking ahead, several improvements can be made, adding more audio feature, leverage larger or more diverse dataset, experiment with different transformer architecture, etc. Thank you for your attention. We've shown how we combine audio spectra and textual metadata to predict songs popularity. If you have any questions, we'll be happy to discuss them now.
Thank you. Bye-bye.